Okay, now we're recording.
Wonderful.
Just do the see the share because I saw the green outline.
Awesome. Well, so we are the Rapid Action Camouflage Deployment Team, or RACT. We are composed of 14 members, and we're going to introduce ourselves again just for everyone on Zoom. But I am Ashley. My teammates are
Adrian,
Chandler,
Gavin, Aaron,
Addison,
Sam, G,
Ganson, Joey, Diego,
Rhoda, Hannah.
Matt.
So today we're going to present to you our design that we have been working on throughout the semester. And our semester was from the middle of May up until this point. We're going to go through our hedgehog concept for you, the customer need that we received, how we put those into our design, through our design overview and key design specifications, give you a few of the design highlights, what we feel is really important about our design, provide you a cost summary so you can see the cost of the system, and then also go through our performance evaluations that we conducted throughout this semester to test our deployment system and make sure it works to fit your needs.
Okay, so let's talk about our hedgehog concept. Our passion was keeping soldiers safe in dangerous environments. We did that by focusing what we're best at, which is integrating mechanical design with real world military experience, while keeping in mind our economic engine, providing rapid solutions in tactical situations. And we distill that into a mantra, which is providing a fast, safe, and reliable camo deployment solution to military personnel.
So prior to any conceptualization or initial design of our system, we generated a list of customer needs and design inputs that our design needed to satisfy. So we analyzed the current process, which you can see right here, and we kind of took the inputs of that process and tried to reference those for our current design. So the customer needs and design inputs that we came up with include the following. First and foremost, we wanted to minimize the man hours required for setup, deployment, and takedown. The current manual process requires an estimated 1.5 man hours under ideal conditions. And greatly reducing this man hours for deployment would not only give soldiers more time and opportunity in the field to be doing other things, but it would also mitigate the risk that they are exposed to in the battlefield. So next we have reliability, repeatability, and durability. And so we want to make sure our system was reliable and repeatable. So that means that we needed to have as little failure points as possible. And so therefore we decided to forego any electrical or motorized components in our system, and we decided to go with mechanical power instead. We also wanted our system to operate under extreme environmental conditions. So freeze, sand were two that we're especially concerned with, and that we decided that we would specifically design our system to ensure that it would be able to operate in those conditions. And then we also wanted durability in mind when we were designing. So all the stress, failure, and fatigue calculations that we performed needed to exceed the minimum material parameters that we selected. And we also aimed to select the lightest and cheapest materials based on our calculations. So simplicity was another requirement that we designated for our design. We wanted our system to be as straightforward as possible, making it intuitive for soldiers to use. So we decided to achieve this through modularity. So essentially, we wanted the design to be broken into compact pieces for easy storage and quick assembly. And also it would allow for maintenance to be able to happen if needed. Another thing we wanted was the design to be external from the vehicle. So we didn't want the design to be fixed or attached to the vehicle in any way, and we didn't want any modifications to have to be made to the vehicle for the design to work. And then finally, since this semester, we designed the prototype as a 1/6 scale model. We didn't do the full scale. We wanted this prototype to be as accurate to the full scale as possible, such that all testing performed on the prototype would be reflective of the actual performance of the full scale model.
All right, so now we're going to talk about the design overview. our design is comprised of 4 independent sub-assemblies. We have the winch, we have a lever arm, we have a roller arm, and we have a base plate. So firstly, the winch is designed to rotate this lever arm about this pivot joint right here, using a steel cable that's actually attached from this point over here. A soldier will crank the winch and initiate that rotation. It actually gets to a maximum height about 60 degrees from the horizontal. Next, we have the lever arm, which is this arm right here. Its function is to provide stability for the roller arm, which is number 3. When it's moving upwards, we don't want the netting to become tangled or creased. So that's why we have that lever arm. Next, we have the netting roller arm. Its job is to provide a efficient and quick release mechanism for the netting. So similar to like a paper toilet roll, the soldier will pull one side of the netting and it will actually unravel the entire netting over the truck. Lastly, we have the base plate over here. Its job is to provide stability for the entire system simply by driving the truck over this base plate and using its weight. It will ensure stability for the entire system.
So next I'll talk about our key design specifications. And I talked about the customer needs previously, and I'll kind of talk about how our design specifications achieve those customer needs. So first, we tested the 1/6 scale model prototype in extreme conditions, like I said, freezing and sand conditions. And all testing was favorable, and we can confidently say that the system worked in these extreme conditions. We tested key components of the design that would be most likely to undergo fatigue or failure due to fatigue, and proved that this system will last a minimum of 3 years under expected loading conditions. We performed a time study that indicated 0.043 man hours required for setup and takedown. And this greatly exceeds the 0.5 man hour requirement that we set for this parameter. And then also the time study indicated that it took 0.021 man hours for deployment, which greatly exceeded the 0.75 man hour requirement that we set forth. We carefully chose our materials such that they were lightweight, but also would withstand the stresses that we calculated. And we'll go further into those stress calculations later in this presentation. But most of the materials that we ended up selecting were aluminums and then a few steel components. We implemented a modular design that utilized quick release pins for all temporary connections, so that when they're in the field, they can quickly connect all the parts, put a pin in, and when they're ready to take it out, they release the pin. And we also used common fasteners for all permanent connections, such that it was easy access for maintenance and repairs if that was necessary.
Going into the design highlights, we first have the drive plate. So with the drive plate, we have an 11 gauge steel sheet metal. It's about 1/8 inch thickness. The purpose of the 1/8 inch thickness is to endure the support of the weight of the vehicle and also any malleable terrain. And then it's capable of withstanding about 141.9 in horizontal and 123 in the vertical direction. So we have this 90-degree angle to make sure once the lever arm is in, no matter how much tension it is, it won't come right back out. And then we were able to get a 2.76 factor of safety and tension at 60 degrees.
All right, so this is the winch we went with. This is an off-the-shelf part. We opted for a worm gear design because it self-locks. That's a good safety feature, especially for high weights. We don't want it to drop in the middle of the process. We're estimating the load that it is lifting about 170 pounds, give or take. It is capable of over 2,000 pounds, so it's well within reason. Because of the 40-to-1 gear ratio that it uses, the equivalent crank load that someone's supposed to output on it is about 4.25 pounds, which is relatively small. And this would take about 63 seconds, give or take, based on our cranking calculations at 2 winch revolutions per second, which is consistently what we were using whenever we were doing testing. It's retracting 32 inches of cable, and that's about how long we're expecting it to take.
So the length of the lever arm in this full scale design is 12 feet. So this meant that there was a big need for modularity in the system, and we achieved this using a steel quick release pin that you can see there. And this is done by having a aluminum support block fixed to the inner arm of the lower lever arm. And then we use the quick release pin to attach it.
All right. So the total cost of our 1/6 scale prototype came out to be $391.53. And the total cost of this was subsidized through materials that were found throughout lab. The manufacturing estimate for this came out to be around $32.75 based on the manual labor from the member of the teaching team. Additionally, the assembly time was estimated to be around $1.69. This is based off of the Boothroyd Dewhurst assembly chart that was outlined in the final design report. For the full scale prototype, the total cost of this came out to be $1,521.16. The total cost of the materials encompasses everything in a full scale mockup. The estimated manufacturing costs, the labor rate for that is $65. So that's reflected in this chart. And additionally, the assembly cost estimate is the same as before, $1.69. So the per unit cost for 1,000 unit production run is projected to be around $1,195.16. This assumes that the vendor does not give a discount for buying in bulk. Additionally, in regards with manufacturing, this assumes that there's an optimized process to manufacture this. So with the use of CNC machining, and with this, we also assumed that the cost to set up the CNC machine is negligible, and the cost for a CNC technician could be around $30 an hour, and the estimated manufacturing cost for that is around $45.50, and the assembly cost estimate for this is $1.69. And despite two of these figures being over the customer needs for budget, we have outlined an improvement plan in our final design report to reduce costs in several ways. And some of them that I will outline is that we have a plan to reduce the amount of variety of fasteners and bolts that we have throughout the design. We also identified parts that were over optimized or not optimized for the design. So those things will be optimized in the next iteration. Additionally, a member of the team was able to identify, in regards to the roller rod, a material that was that cost less but exceeded material properties for that. So, and with this, we will move on to the performance evaluations.
The performance evaluations were to make sure that particular customer needs were being met. For the scaled model testing, the needs that were being tested was scale and accuracy, making sure that the 1/6 model is representative of the full scale model. Attachment, making sure that the system does not require any permanent attachments to the vehicle. Deployment automation, making sure that the system is decreasing soldier involvement and eliminating soldier exposure when deploying. Electrical power, making sure that the system does not utilize vehicle power. And materials, using the same nets that are used in the current system in this system. The testing was done on a grassy terrain and by fully deploying and retracting the system. The photo shows before deployment. Next slide. And then after testing, the evaluation showed that scale accuracy, attachment, electrical power, and material needs were completely met. And for deployment automation, it does decrease soldier involvement, and it also does require soldiers to leave the vehicle. They can use the vehicle as coverage as well. That photo shows the fully deployed model as well.
Yeah, so we conducted environmental testing on the product. We did this in order to address customer needs number 10, which basically states that the camouflage must be deployable in all terrain and various weather conditions. So we did 2 environmental tests, one being the sand grit test as shown here, and the other being the freeze test, which will be shown later. So both of these tests were performed solely on the winch here. We expected that to be the most affected part by environmental conditions. So yeah, for the sand grit test specifically, we wanted to test the winch's ability to crank in a desert-like environment. What we did was we cranked out 48 inches of cable on the winch. We then doused it in water and then covered it in sand. And after that, we had a designated cranking person to retract that 48 inches, and that was timed and recorded as shown in the next slide. So yeah, so here we have the sand grit cranking test. We did we did determine a baseline cranking time for the winch for 48 inches without experimental variables. And that came out to be 1 minute and 25 seconds. And if we were to watch this entire video, we would see that the sand grit test cranking time also came out to be 1 minute and 25 seconds. So basically this test showed that there was no change in the winch's ability to crank because both times matched. And yeah, so this test was ultimately deemed successful in addressing a portion of customer need number 10. And we will move on to freeze tests.
Yeah, so the next test that we performed, as she mentioned, was the freeze test. So essentially what we did is doused it in water, put it in the freezer for 48 hours and let it sit there, and then took it out of the freezer, which is that picture on the left. And after we did that, we did retract it the same way as a sand grit test, and we did that 48 inches. Did the same time test on it. So if you go to the next, this is showing it being retracted out 48 inches. So this was also found to be the same time, 1 minute, 25 seconds, no interruptions in cranking. And we were sure to do the test, as you can kind of see the bits on there, but right after it was taken out of the freezer, so we could simulate that freezing environment properly.
All right, so our next protocol was to test for fatigue. And to do this, we were given a tensile testing apparatus. We purposed this to become a cyclic loader to test for fatigue. The extra hardware that we added was a stepper motor driver, an Arduino Uno, and clamps to secure this apparatus down. All right, so to predict the performance of the full-scale model with small-scale specimens, we had to perform similitude analysis to reflect the forces that we want to induce on the small scale to represent the full scale model. And to briefly sum up the theory behind this, we use the von Mises failure mode theory to sum up the stresses. And on the left-hand side of the top equation, that sums up all the forces seen in the full scale model. And on the right-hand side, if you move down to the second equation, we isolate a single stress value, and that is the stress value that we will use to model onto the small scale specimen. And with this stress, we can find force, and with force, we can find deflection. And with this deflection, we can convert this to the amount of steps that the stepper motor can move. So we can deflect, or we can move a certain amount of steps to induce a certain amount of force. And our first study was the support beam arm. And this support beam arm is 12 feet in length. It's 2 inches by 4 inches. It's made out of aluminum. And the small scale specimen that we decided to test on was a 9-inch length and 1 inch by 1 inch. It's also made out of aluminum. And Joey will be talking about the results that he found that he calculated and found.
Thank you. Following the analysis, the constant perimeter, the maximum von Mises stressor was calculated to be 6,864 psi. The force needed to induce these stresses on a small model was determined to be 97.73 pounds, which is equivalent to a deflection of 0.029 inches. Therefore, the step motor has been programmed to move exactly 59 steps upward and 59 steps downward for each cycle. Okay. The fatigue test result for the support beam shows that no crack developed, either no yielding occurred after 10,000 cycles. The SN diagram representing the support beam shows that the reversible stresses acting upon the full scale model stay well below the curve, indicating a high factor of safety in the support beam design, ensure proper functionality for 3 years.
So our second study was on the roller rod. Its length is 6 feet, and it's a 1 inch solid diameter shaft. And the small scale specimen that we were testing on is 9 inch in length, it's 1/2 inch in diameter, and the thickness is 0.05 inches. And Joey again will talk to you about the results.
The same testing procedure was also applied to the roller rod. The maximum wall misses stresses was found to be 56,576 PSI. The force needed to induce these stresses on a smaller scale was found to be 60.68 pounds, which is equivalent to a deflection of 0.11 inches. And the program is programmed to move 223 step upward and 223 step downward for each cycle. The testing results shows that no crack developed after 10,000 cycles, but yielding occurred due to the step motor drifting. That means the motor was applying more deflection than it's supposed to, cause the specimen overstresses, and then yield the specimen. The S-stand diagram representing the roller rod shows that the reversible stresses acting on the roller rod still stay under the curve, indicating that it will not fail within 3 years periodically.
So our third study that we were going to perform were the bolts that were connecting the tie hook. And we performed hand calculations to see how much force we would need to output onto the bolt. And we realized that there was a high factor of safety against pre-flood. There was a high factor of safety against joint separation. And thus, we decided to omit this from the fatigue testing analysis.
All right. So the final test we performed was a time test with the full 1 to 6 scale prototype. So what we did was we conducted 3 separate tests, one on the assembly, one on the concealment, one on the disassemblies, with 2 builders that were designated for every single test. We maintained the same builders. Each test was video recorded and timed with a stopwatch, basically doing like a 3, 2, 1 go, and then they started building. The times we found were for the for the assembly and disassembly was the exact same, and it was 1 minute and 17 seconds, which is equivalent to 0.043 man hours. And for the concealment time, it was found to be 36 seconds, which is equivalent to 0.021 man hours. Adding these up together and then comparing it to like what was expected from the design requirements, this is 11.7 times faster than what was expected of us to do, which makes us very confident that when we apply this exact same model to the full scale, it will meet the requirements.
Here we have an assembly video, which acts as a visual representation of the builders basically removing the components from the wagon, laying out the base plate, affixing the lower, affixing the roller arm to the upper portion of the lever arm and the winch to the base plate, and the full arm assembly onto the base plate. And they're basically gonna put the wagon onto the left portion of the base plate to hold down the structure. And the builder number 2 is gonna fix the hook of the winch on to the holding tie, the tie down, and basically crank the winch to roll the lever arm up to that 60-degree angle.
Yeah, it does take a little bit for the winch to fully engage. So you can kind of see here, but then once it does, it moves up pretty fast after that point. So once it gets enough grip, then it comes up and it starts moving pretty good once you start it moving.
The total approximate time of the assembly video recorded was 1 minute and 17 seconds, which
Yeah. Didn't like that.
In this video, we have the concealment process to where the support poles are placed out after the vehicle's after the lever arm is rolled up to its correct position. The net is gonna be unfolded and then the support poles are gonna be placed underneath the net to distort the shape of the vehicle underneath. And this took approximately 36 seconds. As you can see, we only had like a small portion of net to work with, so it doesn't fully cover the vehicle, but it's just giving a demonstration as to how this would function in the with the full scale assembly essentially.
Right. So that concludes our presentation for the slides we have, and then we want to see what questions that we can answer for you guys today. If we need some time to think about it, we actually have our system here and we would love if you guys could assemble it. So we wanted to give you guys hands-on experience with the system. And just so you guys can see how the components move, see how they go together, and actually just get some practice with it. So if someone can grab these forearms, I'm gonna take all the parts out and roll the wagon out.
I'm wondering if there's a way, like, to record you as you're doing that.
If you want to turn your, I can stop sharing my screen here. And if you wanted to, yeah, we can turn someone's video on and then do that. Yeah. Where's my video? There we go. Oh. What if we do it on the table? Here, we can assemble this on the table. So if you guys just want to lay the pieces there. Yeah.
Yes. Yeah, we've got.
Yeah.
Can you guys like move more to the middle? Because like, there's just too many tables.
Yeah, here, we can just move the computer right
Oh,
here.
sure, it's connected, I'm sure if you need it.
Can you see that, G?
In your guys' final design, I recommend just doing A to A, B to B, and literally just writing it, sharpieing things. Trust me, we've got soldiers that, although you'd think should be smart, if you make it dummy proof for them, makes things much easier.
So like on the,
Yeah, I'm actually.
A to A, so if you just put 1 to 1 or 2 to 2 or something like that, trust me, your life's so much easier and
so do you guys want to actually assemble it or do you want us?
with the fit in, I mean, this is just what goes over it to lock it into place, right? And I'm guessing, sure, quick release. Should just go. There.
We've got the stopwatch. Right?
So one of the things we noticed and actually is in our improvement plan is that with the 90 degrees, if it seats, you have an issue where a side of it comes up and this roller arm won't be straight. So one of the parts we have in our improvement plan is to make this just a straight slot. So to show what the system would actually do and have it deploy successfully, we actually put, I think it's bearings right now to just fill the space.
Okay.
So it won't seat all the way down, but it'll be straight.
And then once this is down, I'm guessing just.
Yes, sir.
right through that.
All the other two, like the parts you would never lose the.
Yeah. No, I really like this.
Last part is attaching, right? We are doing the time. I'd have to.
So yeah.
Otherwise. Thank you. Let the see.
Yeah.
With the way that you deploy the camouflage is, do you guys have those little poles too?
Yes, we did.
That I'd recommend, at least for your future things, is what you can do is you can set up these back poles first, and then you can have it drive in on top, if that makes sense too. So that way it just. Because what I'm imagining for you guys is you guys have already prepped this before the vehicle pulls in, right? So as much of that prep that you can do beforehand, if you can do those back pulls too first, that way it's already ready. And you just put those front two in after the vehicle pulls in, if that makes sense.
Right, yeah.
You can just put
the drive plate right in front of the front wheel, so it just has to roll like.
Yep, and so ideally, this would be. Your, obviously I can't stick these in, right? They're pretty little, but. So that'd be my one recommendation for your. But yeah, anything like that, because the less time that you can have with that vehicle being there in the open. It's a big thing, at least with our paladins, the way that we move in, which are artillery pieces. You have to be essentially like dug in like 15 minutes or something like that. So the more of that stuff that you can prep before you even get there, the better off it is. Which again, it's not adding a ton of time, but 1-2 minutes is very helpful. You got any comments, Randy?
Just initially on weight didn't see overall weight listed on the.
So overall weight of the system, not including the netting, we estimated to be about 60 pounds is what we said.
Yeah, about 60 pounds, and netting's about 150 or so pounds.
And that's for the full scale.
What's the separation between the weight between these two?
So the
And then the base.
so the support arm is about, what did we say? It's 12 feet, but then the weight is like 19 pounds. The roller arm is like,
Yeah, it's maybe 9 pounds, it's steel, so
yeah.
it'd be a little heavier. All the aluminum parts are significantly lighter.
Yes. So actually a big portion of the weight is from that steel support arm for the winch and then for the base plate. And the reason that steel was used for the support arm is because we have the winch welded to the support arm. So if you wanted, another thing that could be looked into if we wanted to reduce the weight even more would be kind of attaching that winch with fasteners instead, so you didn't have to weld.
And what about, the cranking on the winch? Did you think of any other options for minimizing the cranking or?
It is compatible with a cordless drill. I understand you don't always have access to that. That's why there's always the backup for manual. But with a cordless drill, that can just 19 millimeter bit attached to the end of it, socket head, and it can drill it up, spin it up really fast.
The other option is, didn't we talk about switching out the gears too for the winch?
Yeah, switching out the gear ratio. Right now it's a 40-to-1 gear ratio, which is significantly more than it needs to be. Ideally, it'd be like a 10-to-1. That's if you were to manufacture your own winch. This is an off-the-shelf one, and it's relatively cheap. So ideally, it'd be a 10-to-1 gear ratio, and it should take 4 times less cranks. That would put an equivalent load of about 17 pounds on the handle for somebody to crank up, which is still relatively in reason for someone who has to take a physical fitness test a year.
Yeah. I really like the idea that it's multifaceted too. So a common thing that you'll see is somebody's multiple things will break for multiple of these. So if you've got like 20 different of these and say mine breaks yours and yours breaks there, at least, hey, we can put ours together and still use it. So that way you don't have a complete system fail, if that makes sense. Right. So I'm a big fan of that.
I see on, the design here, you got nice rounded edges with the purchase part, but no rounded edges on here. Is that included in your design or?
And that was just for manufacturing sake because we manufactured in-house, and so we had like another student, a TA that was manufacturing for us, so we just didn't want to do like fillets and stuff that were unnecessary, but like if we were to make this a production part, we would definitely make rounded edges so people don't cut themselves.
Okay, so that's a typical design engineer response to blame the manufacturing guy.
That is something we noticed on especially this pivot joint. And so if you actually feel the edges on the pivot joint, they were rounded because we had that issue come up. So it was something we need to add to the drawings.
So it's not on the drawings yet?
I don't,
So it's not the manufacturing. No, okay. The manufacturing guy gets the blame.
Was there any consideration for, I know that you guys did weathering for sand and freezing. Was there any consideration for just leaving it outside for a year? And like, if you just left it outside, like how will the winch perform and stuff like that? Again, I know that you probably want it kept inside at some point. I know my soldiers, I know that this stuff will sit in the back of an open truck at some point for months on end. What would be the biggest failure point if that was to happen?
We still think the winch is the most viable to fail over time because of the constant mechanical contact. We have looked at other winches because that's just an off-the-shelf part. It'd be easy enough to buy another winch. You can buy like a cable strap winch one for cranking a boat onto a trailer. That might be a little more weatherable. So we have looked into other options like that, but any of them should work. And a worm gear usually doesn't fail because of the motion it incurs, so it shouldn't have a problem with that. And most of it's galvanized steel, especially that steel cable is galvanized, so it should resist corrosion at least for some time.
And then just the last part, and I think I failed honestly, you guys with this, but I should get you guys, if I can, what's known as a BOM. It's like basic materials that we have on hand for like screwdrivers and stuff like that. For certain key parts, like these screws and stuff like that. Hopefully I can get you guys what wrenches and stuff like that we have in the field. So just if you guys would be open to in the future, just changing up potentially some of the screw sizes or something like that, just to fit the tools that we do have on hand with most of the vehicles. I saw that you guys had an LMTV. I can try and get one of the parts, or one of the, again, I'll call it a BOM. It is called a BOM, but it's just, hey, what tools do we have that comes with that vehicle? So just know that for future designs, maybe you might have to, or you might want to consider changing the screw size or something like that to fit the tools that we have on hand.
And like we were talking about previously, we're trying to condense and make the fasteners more consistent. So if we know what we have, you can make it all the same size, consistent with what they have on the VAI.
Good.
Okay, let's bring some questions on the slides.
I'm scared. So it's my fault. I think I didn't reply the email very carefully last night. But so on the slides of you changed last night. I think there is some mistake there.
Talking about the similitude analysis.
Yeah, the structure part.
For the benefit of record, share the screen again.
oh, yes, I can do that.
Yeah, this size. So you have let me see. This one sigma y normal stress in the weathering caused by bending. First, this XY coordinate and you have local X coordinate. Don't get confused coordinate here because global XY coordinate is global coordinates, but here I think your X should be in the X direction, local X direction. So don't like, okay, this is X and this is also X. There's only one coordinate in this graph. And also, I think I told you like at like normal stress caused by what? Sigma XX is caused by bending. Why there's sigma Y caused by bending?
It's a zero. It's a zero in the equation. I'm writing now because it's a part equation. But in the equation, the value is a zero.
Okay.
Yeah.
But I know it's 0, but it's not correct to say normal stress in the y direction caused by bending. If you think about this thing, you have bending of this beam. Can any bending situation cause sigma yy? No, no, impossible. You can bend in this way, you can bend in this way, bending in any direction. There's only sigma x. What can cause sigma yy? I push it or I stretch it in the y direction, sigma yy.
Compression.
Yeah, bending cannot cause sigma yy. Bending only cause normal stress in the x direction. So it's, I know you say, okay, it's 0, that's fine, but it's not correct to say that the sigma y is caused by bending. Right? And also, as I said in last Monday's class, it's like shear stress x y caused by the torsional transverse shear is better. You make like specific for design. Is it torsion or transverse shear or and both torsion and transverse shear?
For our design, it's mostly torsion because the transverse shear on the top surface 0. Am I right? The transverse shear on the top, it's 0 because the first law of inertia.
Yeah, y component here. It's
Oh.
0 now.
Okay, thanks.
Right? You have a y component, you have reaction force, you have y component here. So it's better like specific for your design. You both have torsion and transverse shear. You cannot just like test with general information here, torsion or of course I know torsion can cause torx y, transverse shear can cause torx y, but this is presentation specific for your design. Yeah, but it's a great. I think overall the presentation slides, everything is like a lot of improvement since the Monday's class, so that's good. And also I like the video of the like particular testing. Yeah, that's super nice.
Thank you.
So that's my comment.
For the presentation, just when you answer questions, be confident in your answer. Don't ask, am I right? You know what right and wrong is. Even if you don't, you do for the presentation. I got this. Trust me, I'm still working on that myself, but
It's okay, stressful. Thank you.
Get a lot of, I'll get back with you on that. We'll find out the answer.
so there's times to do that, but if you do think you know the answer, or if like the thing,
Yeah, if you're
like
talking
you're
about
the expert. Yeah, so you can respond with a, I'll get back to you later, and then make sure that you do. But if you are answering the question, you know the answer. You got this. So don't second guess yourself. Like you'll do great.
And does Rick have any question? I don't know if you're.
I do, Matt.
Yes, it should be on. Oh, wait. Let me
So can you hear me? Can you hear me?
No, he's not muted.
Check your source for the thing, because you have the HDMI cable and it might.
That might-
go to the TV.
Can you hear me?
Yes.
Okay, cool. So probably the thing that I struggled most, I know you've got the customer there in the room, but it would have been nice up front if you'd have shown me what the requirements were that you were trying to meet in the project, like the actual numbers. I picked them up as we moved through, right? That you basically had half an hour to deploy and set up and take down, but it was not clear to me up front that those were the specific requirements. So something up front that kind of shows what are the targets that I'm trying to hit. The same thing, I wasn't clear on what the cost was that you were trying to hit as well. You talked about being beyond the cost, but I didn't know how far beyond because I didn't know what the actual requirement was. Let's see. So you did the time trials on a 1/6 model. Was that 1/6 in all directions or just in a particular direction? I was trying to picture exactly how high of a vehicle we're trying to cover.
So it was 1/6 scale in terms of the lengths. We didn't scale down the cross-sectional area because when you get into scaling that down, we found a lot of issues with finding bearings or fasteners that would do what we needed them to do and be of a proper size. So it was mostly scaled down 1/6 in terms of length.
Okay, because what I was trying to picture is is there anything that someone needs to get up on a ladder or whatever in order to help with the deployment onto the poles because of the height of the vehicle that it's trying to cover? And I just didn't have a good feel for that during the presentation. I love the videos that y'all gave showing the deployment of everything, but just understanding how that translated into the full scale would have been helpful.
Yes. Oh,
no, that's okay. Go ahead.
I did have an answer to your question about if there was
Sure.
anything anyone needed to get up on a ladder for. And so that's what we specifically had in mind when designing the system, is we didn't want soldiers to have to climb up onto the vehicle, lift that netting above the vehicle itself. So there is nothing that you would need a ladder for. We're part of our improvement plan is attaching rope to the end of the netting. So it'd be something that wouldn't need to make any holes in the netting, but would attach the netting in some form. So then you could just pull it over the vehicle.
Okay. All right. And then y'all talked about failure when you were talking about the fatigue failure. It seemed like y'all defined failure as cracking, but then you had yielding of the specimen that you were testing. You know, yielding can be considered failure as well. So what was your failure criteria? Like what did you have to avoid doing in order to be able to say that you did not fail?
So I'm gonna let Anton talk a little more about that.
So mainly we are testing for just cracking. Yielding was a thing that we observed while testing, which is not supposed to be happening. We designed the system that it is well under the maximum yield strength of the material. So it's mainly just cracking that we were testing for.
Okay.
And
You observe yield because the test had a malfunction and
Yes.
yes. And then didn't we also test on the hollow tube instead?
Yes.
So there was one of the points was that with the testing, there was deflection in the motor, right? Or drift. Yeah. And so there was more stress put on the material than intended. So that was part of it. And then additionally, what we were testing was a hollow tube that had a specified thickness of
0.05 inches.
0.05 inches. And so when we redid our hand calculations for that tube, we found for the 1/6 scale, it worked, but for the full scale, it actually did fail. So that's why in the full scale model, we went to a solid tube, is because of those yielding results observed during testing. And then also the hand calculations we redid. So that's why we upped to a stronger material that was solid for the full scale.
Okay. And then if I understood right, the base plate that you have, I know it's for stability of the device, but it's also something for the vehicle to drive on, right? To hold it in place. Is that correct?
Yes, sir. So that's how the stability occurs, is because the weight of the truck is what weighs down. And so the base plate just gives the truck something to drive onto.
Okay. So I guess my question would be, for the final designer, you're going to have some sort of mark on the base plate that you need to make sure that the wheels cover in order to make sure that you're in the proper orientation before deploying the netting?
Did we decide on a marker? Is the base plate just wide enough to where it would fit the wheel? So there isn't a mark right now. The way the base plate is designed is it's just wide enough for the wheel. So if you could see the base plate, then the truck wouldn't be on enough.
Okay, fair enough. And then I do question, yes, galvanized is going to protect it from the environment some. I would question whether or not, especially in some of the harsher environments out there, whether or not that galvanized would hold up over time. So you might want to also explore potentially putting some sort of coating over the galvanized steel as well, just to give it an additional layer of protection. Overall, I thought you guys did a tremendous job. I could follow along very well, even when I didn't know exactly what the requirements were up front. I could, by you explaining things, I was able to catch on as it moved through the presentation. So good job.
Thank you so much, sir.
Okay. Any other questions, Dr. Prasad or Alex?
So just let me ask, so I'm a human factors guy. So what do you think you could do to improve or make it easier for the soldiers to set up and assemble the device? So I noticed, when you scale it up, of course, the soldiers were strong guys, but you want to reduce the burden on them. So this would be a big, heavy thing. What can you do to make it easier to grasp, pick up, to put down, to assemble? We addressed some of the safety issues before, right? So that is sort of included in that, but in terms of making it easier to, deal with on the field.
So I know some of the parts we have in here were specifically for that reason. So that's why it separates into so many pieces, is so it's easier for them to carry. Because in order for the system to be able to reach above the height of the vehicle, it has to be pretty long. And so that's why we have the modularity, is to separate it into smaller pieces. One of the things that was discussed right at the beginning of the presentation, a suggestion we got, not at the beginning of the presentation, but at the beginning of assembly, is actually labeling on the parts. So stating like the mating connection points, having them have the same letter. So then you just match letter to letter or number to number.
But in terms of, you can ask your clients because they're here, in terms of trade-offs, so design is about trade-offs. What do you think would be easier? Having something that disassembled into multiple parts, but the disadvantage is that you have to, you're in the field, you have to find all these parts, put it back together, or something that is bigger with less parts, it doesn't disassemble, but the trade-off is it's heavier, you have to lift and move with two people. Which direction is the better direction, you would say?
I'm a big fan of the modular, at least. Some people obviously would go with one piece, but I'm a big fan because what you have when modularity happens is one piece breaks. I don't need to replace the entire system. I'm a big fan of replacing individual parts rather than systems as a whole.
And many fasteners are okay on the field?
I'm a big fan of fasteners too, because I've seen people make do with fasteners before. It hasn't always been stress tested. It's, hey, let's get something in there and like it'll still hold and be able to do the job for the moment. So that's why I'm a big fan of the fasteners too. I think that they're easy to replace, easy to find something to just go in there. Soldiers will make do sometimes. So that's why I'm a big fan of, if you make it modular, and again, if you have two of these now, if one part of one thing goes down, I can now say, okay, rather than having two broken things, I can now have one working and one broken, kind of scrap it for parts. So that's why I'm a big fan of the modular.
And last thing, what about maybe handles on the base plates or things that have to grasp? And secondly, safety in terms of the winch itself. So you're doing that, but I mean, if your finger gets snagged in an environment, covering up the winch itself in some way, what are ideas on that issue?
So that was something we did look into, is winch covers, more for environmental, but for safety, it would be another concern that would address. And again, it would be researching what winch works best for you, or making a part to cover that. Because obviously if you made a cover, then the handle would begin to interfere. So with this winch, it may not be possible, but being able to find a winch that, if that was a major concern in terms of safety, finding a winch that does have that cover.
Do you think that will be a major concern?
Not a major concern. At least my unit, we deal with a lot of heavy machinery. There's a lot of other things that I'm much more concerned with my soldiers doing. When operating this, they should also be wearing typically at least your helmet, your eye pro, and gloves is what I would just recommend. It's pretty standard for us.
So the lesson here is the clients here just work with the users and sort of what will work.
And as long as you just mentioned beforehand, okay, wear gloves, so that way you don't snag a finger in there or something like that, or don't wear jewelry. I mean, pretty used to just being told that. So as long as you just upfront say that, that'll probably mitigate most of your problems.
Okay. Yep.
Thank you.
There was a pretty long concept ideation period in the beginning, and you went through a lot of different concepts before ultimately landing on this one. And this is a pretty common question that I ask all mech 3 groups at the end of semesters, and this is not a trick question. If you were to start this design completely over from scratch and do another semester of mech 3, which I don't wish on any of you, I want you to look at it. But if you were to do this project over again, do you think you would arrive at a very similar solution? Or now that you've done it once, would the second round of a brand new design look completely different? Do you think that this is towards the optimal design for this solution or for this problem?
All I can think about is
The
the
drywall lift.
drywall
Yeah.
lift.
I don't know if you're familiar with like sheetrock drywall lifters, but they're capable of lifting up to 200 pounds. We found this out like way too late in the process after we ordered every part, but essentially all you'd have to do is get a roller rod, replace part of the top of it, and it just lifts it straight up to 15 feet up in the air. It's just a system of pulleys and cranks. It's made up of 3 parts. There's a stand, a large pulley system with a crank on it, and it has a pretty low gear ratio, enough that it goes up very fast within like 15 seconds, and then it would just be up at the top, and then you would just have to unroll it from there.
What the cost of one of those?
I think a cheaper one is like $250, but a really good one is a lot more expensive than that. So it may be harder to disassemble with a cheaper one. I think the higher ones are usually for rent, but if you were to purchase it, it'd be about $1,000. But it's just all dependent on budget and that kind of thing. Otherwise, you could look into the design of it and try to manufacture it yourself in a more easy way. So it's just straight vertical transition upward. So that might be easier to implement, but that's the only thing that we sort of figured could go better than this.
Yeah, I remember sitting down with Gavin many hours at a time at night, trying to figure out many new concepts to make this work. Ultimately, I hated to admit, but I really like Gavin's idea of just the lift for the drywall. But we were definitely too late in the process to try and change designs. So, yeah.
That would have been something I think we would have researched more if we had the time. And just seeing if there was a way to make it cost effectively or find one that is cost effective. But also in terms, I think our next, like the next one, if we couldn't make that work, would be this system unless anyone has a differing idea. And I think some of the changes would be just rethinking the pivot joint again. So this, see if I can turn this. So this joint right here, making it so it doesn't have a divot, so we don't have that lifting issue. And then again, just rethinking the gear ratio for the winch, where the 2 biggest parts, like if we had more time or could start it again, it would probably be a system similar to this, but with those parts being a little bit different.
Just keep in mind with that 80% solution later on, so. Again, at least in my job, like, hey, get something now, fix it later, and you'll do good enough. So obviously you guys had a time constraint, but if you redo it better with the things that you considered there.
We had a lot of issues with just the sheer moment arm of how long it is, because in the actual design, it would be 12 feet long, and the tension of the cable trying to pull against that as it's lifting was also a huge concern. So we were trying to address that in many ways, and this is how we set about with that. But thinking about like with a drywall lift, it would just be vertical translation. There wouldn't be as much of a moment arm. It would just be
That'd be ideal.
Yeah, one of the original ideas that we tried to branch off from was having 2 12-foot poles attached to the ramps and having the vehicle drive over it.
Catapult.
Yeah, it was basically a catapult, and we really discovered that it would not withstand the dynamic velocity when it would do that. So
It's also just a hazard.
big slingshot, launches it up.
Anybody standing.
Just based on the size of the wheel, moving like half of an inch forward is immediately like a large transition.
Yeah.
forward.
I think we did calculations, and again, they were kind of rough calculations, but like even if the truck went 1 mile an hour, the thing launched up at like 35 miles per hour. It was just.
Okay. Any other questions, comments?
Just a quick question for you all. When you get systems into your shops, do you have like some type of coating or concealment that you do to your devices to make them blend in with the terrain? Like, do you have
Paint, grab brush from wherever you're around. I mean, it all depends. I hate this answer. It's called METTC, mission, enemy, terrain, time, civilian considerations. There's one more T in there that I'm forgetting. It literally all depends. I've done everything from. We had paint on hand and we're able to paint it up well before we got to an area. I've done, hey, we're here, grab some fallen trees that look like what's behind us, what's in front of us a little bit. You're constant, at least in my job, you're constantly updating concealment for your time constraints. So there's like a, hey, we've got 15 minutes for concealment. Hey, we've got 2 hours, and you're constantly improving. So, I mean, this is obviously a good start for like that 15-minute, like, hey, we just need something, and then you're always improving your own position. So like, this is the first step. This isn't the last step for concealment, if that makes any sort of sense. If that, did that answer your question? Okay.
I do have one comment.
Yeah.
So I think, well, this is the first time I really in the in-person presentation, because I was hired during COVID and all the past year presentation all on Zoom. This is the first. I think this is super cool. Like, and also the slides like much better than on Monday's slides, and the presentation were really great. And I think I can follow everything very clearly, and there's no crazy thing. Everything is great. Just one thing, not judging you or anything, just like some improvement. Because overall in presentation, well, I think this is also useful for like job interview, or you go to graduate school, you do the research presentation to a conference. Be confident. Because one thing I feel when you do the presentation was like you were not that confident, but you need to think about like you need to be proud of yourself. You are the expert of your design. You spend like more than 3 months work on this and did a great job. So when you do the presentation, you really need to be very confident. The same as he commented when he answered the question. Don't ask me it's right or not. You are the expert, all right? You should be very confident when you say something. And the thing I feel that you were not that confident, and you were like the eye contact with us. It's like you were focused on the screen. So that is not something that you want to try to improve. So like it's a communication with the audience, facing us and talk confidently. And also I was like working as a mentor for the female students in the STEM. So I was like trying to like encourage them how to thrive in like in STEM. And I feel like, especially for our female students here, you should really be proud of yourself in our mechanical and aerospace engineering program. So be confident and do the presentation. Don't worry about anything. I mean, none of us know better this design than you guys, right? So be confident in your presentation. Okay. Yeah.
Anything else?
How many of you guys I heard one of you guys say before, like how many presentations you guys have done? Is this like one of your guys' first like big presentations or anything like that? Or do you guys get a lot of presentations before this?
Mostly to students, to other students, not to like faculty or something like that.
We did have the hiccup of like 2 years of Zoom as well. So a lot of Zoom presentations makes it. I mean, it would make it more convenient for this whole like rotation thing with all 14 of us, but otherwise it's not the same in terms of trying to communicate an idea, at least in terms of nerves. A lot easier to talk to a screen than it is to talk to people. From students.
For you guys, if this is like one of the first times presenting, you guys did a great job of that. So good job.
Thank you. Thank you.
Very good.
Okay.
Thank you so much.
That's the only one for today. Tomorrow is the same time, same Zoom channel.